Q-tensor modeling myself. It's a very useful and interesting way of understanding how the crystals interact with fields, etc. And I believe it's also clicker-tastic, so make sure you've got your clickers fired up and ready to go, because I think there's going to be some audience participation. I'll hand over to Nigel.
Thanks a lot, Tim. Yes, it's a bit early for some hardcore maths, so I will be fairly gentle. So I was asked to do something about Q-tensor theory. Q-tensor theory really is found fashion in the last 5 years, really. It's a bit difficult to explain in 10 minutes I've got left before coffee, but anyway. So in actual fact, what I'm going to do is not really do the Q-tensor theory so much, but just talk about theory. So I'll talk about theory. It's really an introduction to theory and how you model liquid crystals, and I will hopefully come to Q-tensor theory eventually. So yeah, I'm from Strathclyde in Glasgow, really the home of quite a lot of theories of liquid crystals. Frank Leslie's picture you saw before was one of the originators of quite a lot of the theories, certainly dynamic theories of liquid crystals. So hopefully this will be accessible to most, at least partly. Not that many equations. Please ask questions whenever you have them, or feel free to talk to me at coffee. I think I'll probably be here at lunchtime as well, or email me if you've got particular questions. So if I don't finish the talk, which is highly likely actually, given my 150 slides, then I will make it available online. So first thing to do is I want to know where you're from intellectually. So here's the question to ask is, which discipline are you from, or do you most feel more comfortable with, or where do you associate? So I think, what do? I press on the button. Press on the A to E. There we go. So please make your selection now. Let's see how many people we've got in the audience. So we should have at least 40. 40, I think you had 45 there, where are those 3 people gone? Oh dear. Right, I'll finish it now. So quickly make your choice. Okay. Let's see, I do that, don't I? Oh, a lot of physics. Right, good. Oh, one mathematician. Who's the mathematician? Anyone can put that hand up to be a mathematician. They pressed it by mistake, oh no. Never mind. And 2 others. Who are the others? Let me see where you're from. Any others? Put your hand up if you pressed others. Any? No one? Right. Okay, mistakes. Right, okay. Well, physics. Physics, right, okay, that's good. You should be able to understand most of this. Chemistry, you don't do an awful lot of modelling in chemistry, but hopefully a lot of this will be accessible. I'll be talking about phases, and engineers, I don't know, I teach engineers and they generally can't do the maths. Never mind. Okay, so let's just hope. I will come up to some quite engineering kind of aspects right at the end of the talk. Okay, so a quick outline. We're going to say, why do we use models? Why are they useful? In fact, almost every, well, I think probably every liquid crystal display or technology that's used has used models. Either it was predicted before the display was actually created, as in the TN. I'm going to be slightly careful what I say because of legal reasons, but a similar mode of operation for the twisted pneumatic was predicted theoretically from before the device was developed. So they're very useful. I'm going to talk about how to develop models. So really, right from the start, how do I actually develop a mathematical model of a liquid crystal? Lots of different things which I'll go over, but I'll go over these in detail. And particularly, I'll talk about pneumatics. Pneumatics are the easiest things to model in terms of a liquid crystal. There's lots of different choices of theories of models, and I'll go through a particular example of why Q-tensor theory is actually quite useful, and in fact essential in some applications. Okay, so recommended text. So if you are very interested and need to know some theory, then here are 2 books, both in fact by my colleagues at Strathclyde. So Ian Stewart wrote the definitive book on pneumatic and symmetric continuum theories, the basic theories that are useful in displays. Andre Sonnet and Epifanio Verga from Pavia wrote a recent book on dissipative ordered fluids, i.e. crystals, to be honest. And that's got a lot of Q-tensor theory in, so if you want that, then it's there. And obviously, lots of people advertising books at the moment. So unlike Tim yesterday, I have no profit-making ability from these books, so please buy them anyway. Okay, so let's start with some definitions. I want to define what theory is and what a model is. So some people kind of mix these up. For me, a theory really is a set of ideas. It might be modelling a phase of liquid crystal, but really doesn't have an application in mind necessarily. A model, on the other hand, really is looking at a physical manifestation and modelling that, simplifying that to get out some information, some calculation or some prediction. So, slightly go over there, but this is from the OED definitions. And really, so there's a summary. The theory is a system of ideas that I can then develop a model from. So models are always based on theories. Okay. What we need to be clear of when we're making a model is really what the question is. That's essentially it. And this is where talking to experimentalists really helps. So we might want to understand an experiment. We've seen some experimental result. We want to understand what it is. We need to know a bit of physics. We probably need to model that in some mathematical way. We want to discover what kind of physical phenomena are involved in whatever experimental result we have. And we want to predict the behaviour for maybe a different system. Let's say we've seen something happen, and I want to throw in a different chemical. Steve's made a different chemical compound, and I want to, before he's even made it, I want to predict exactly what's going to happen. What that means is I can then optimise. I can say, well, actually, Steve, make a chemical with fluorine in instead of whatever it is. I'm not kidding. So, prediction is a big thing about modelling. So an example, so I noticed from the poster for the iCamp summer school, there was this picture. Okay, so I'm going to use this again and again. This is the Schlieren texture, which Tim Slukin mentioned yesterday. So the Schlieren texture, simply, it's German for streaks, streaky. So these threads here, so remember pneumatic is the Greek for thread. These black threads were seen. But Germans can't speak Greek, so they call it Schlieren. So Schlieren is just this streakiness or thread-like in German. Okay, so let's have a little think about this. So here's an experiment, and we've just literally seen some under a microscope there. This Schlieren texture, these strange patterns. What might we want to explain in this experiment? So here's a question to you. What might we want to explain? Anyone put their hand up and tell me? Yeah?
What are the little junctions?
One of the junctions, yeah, so these black lines meet at some junction. What is that junction? Anyone else? Sure.
What's causing the formation of this?
Yeah, what causes the formation, exactly. Yeah, the structure, maybe, of these things. Anything else? Yeah.
Well, they have different colours.
Different colours, excellent. Someone else over here?
Yeah, the same question.
Same question.
Schlieren texture is on the defects of the
Yeah, so these junctions again, the defects there, yeah, so that's right, you know that there already, these are defects. So I've put down a few things here. So yeah, what are the streaks? What's the structure there? And the size, so what's governing the size here? I haven't given you a size bar on here, but what happens? What happens when they merge? You can see these are merging into defects, as someone knows already. What happens as we change time, as we maybe change temperature? Is it reproducible? Can I heat this up, get rid of it, and cool down again, and does it form exactly the same structure? And white colours and things like that. Okay, so many, many different questions. When you're developing a model of a physical system like that, there is always a level of abstraction. I can't possibly imagine that I might develop a mathematical model which perfectly represents that whole thing. I'd need to know where every atom is, in fact, subatomically. I might want to work out the quantum mechanics. That's just impossible, so I have to abstract in some way. So I have to know what the important details are, what's essential to put into my model, my mathematical abstraction, to actually replicate reality. But we don't really know what's essential. Well, that's where experimentalists help. So experimentalists, we can then do some experiments, we can work out whether things change in time, whether it's reproducible, whether it's always the same size scale, things like this. So experiments certainly tell the theoreticians they hint a way towards the theory. But the most crucial part, and it was mentioned yesterday, I think, and how I work with people I work with who do experiments, is the second arrow. So often experimentalists tell us what we see, we can build a theory around that, and then as theoreticians we might be able to predict, or we might have questions. Maybe what we originally thought were the important things in the experiment turn out not to come out in the theory. So we've got to feed back to the experiments. They maybe do a few different experiments, change the temperature or whatever it is, and that cycle should keep going. And this cycle will never stop. There's always something new to actually understand. Okay, so I've got an example. So we're in Cambridge, so Newton seemed a perfectly reasonable scientist to consider. So here's Newton's famous experiment with a splitting white light into colours. Now this is a picture from the 19th century actually of and it's actually a woodcut print. Now why on earth the 19th century artist decided to do this in black and white, I have absolutely no idea. Clearly we can't see any colours at all. But he did. So after this, people decided it was silly, and they in fact coloured the picture artificially. And so now we can see the colours. Okay, so here we have an experiment. And I might want to abstract this, I might want to build a model of what's happening. So, people knew that when you had a prism, piece of glass, that light was split into the colours. People knew that for a while before Newton. Newton's key thing was, and what they really thought was happening, was that the prism actually had some kind of colouring effect on the light. As the white light went in, it coloured the white light and it came out multicoloured. What Newton showed, and this is his original drawing, was that you can split it into the colours of the spectrum, but then put another prism, it recombines. And so that proves that it wasn't the prism creating the colours. It was something quite different. So that was Newton's main contribution to that problem. But what's essential in this experiment? What would I need to actually, the essential component to then maybe try and abstract this? So I've got it. I think this is a quiz. Okay, so there we go. So you can vote now. So is it just a light in the prism, light prism in your eyes, Neil trousers, as was obviously the fashion, or light prism in a grass? Wait, I can't remember where we got up to, 42 I think it was, wasn't it? Unless someone's coming at the 43, 44, oh yeah, they've turned it on maybe, oh 46! Fantastic. Right, I think we'll stop that one there. And let's see what people think. Right, okay. So, light prism in your eyes seems to be the winner. Personally, I mean, this depends on what you think. A grant maybe is not absolutely necessary. Newton didn't have a grant, he had an awful lot of money himself, to be honest, but he didn't have a grant. Knee-length trousers, definitely not absolutely essential. We could probably model this without the knee-length trousers. In fact, I personally would say B. Okay, the experiment is to split light into colours. Whether we're there or not, looking at it, really maybe doesn't matter. But if you think that we need to be there, then maybe your eyes need to be there or some way of detecting this. But yeah, B or C are probably maybe correct. Okay. So, how can we abstract this experiment? And so that process there of questioning what's essential to the experiment tells us exactly how we could abstract that experiment. And so here is a rather simplified version. It's on an optical table there, but we don't need that. Here we just have white light and a prism, and it's splitting into coloured light. So there's a physical model, and it kind of informs us as a mathematical model that we might just have to model the light coming in and whatever the glass is, the difference between the refractive index of air and the glass. And that will probably do it. Okay, I put this up because I found this on the web when I was searching for Newton and optics. Another model, a physical model, and in fact, there is actually some refraction going on in that glass Lego brick. But anyway, my sons really like Lego, so I put that in there. Okay, so how do we model behaviour of liquid? We really don't want to do optics just yet. Tim will talk about that at a different time. How do we model the behaviour of a liquid? Well, what we could do is think about an atomistic level description. We could think about the atom, a position of every atom, the motion of every atom in each molecule. Okay, so here we have a few little water molecules vibrating around. For a typical liquid crystal device, the number of variables is then very large. Can't understand what's going on here, but anyway. So a region of material, so I've picked a pixel. So a pixel might be 1 millimetre by 1 millimetre by 1 micron, well maybe 10 microns or whatever it is, it doesn't really matter. So that would contain 10 to the 17 molecules approximately. So this, as a theoretician, am I allowed to touch these things? So this, I'm guessing, is maybe another 6 orders of magnitude more than 10 to the 17 molecules. So there's an awful lot of molecules in there. And of course, each molecule itself would have, I've just randomly picked 100 atoms in. Some of the more complex compounds would have 100 atoms in. So 10 to the 19 variables. No computer really, as yet, is going to be tackling 10 to the 19 variables, looking at a kind of phase behavior. So the most we have is atomistic modelling really has been carried out with about 100 molecules, maybe hundreds of molecules, but that's it. And really you're just looking at molecular interactions there. It's extremely useful for those kind of interactions, but there's no way we can model a real device at that length scale. Okay, we could consider a simplified form of the molecule. Okay, so a really complex, so we had our 5CV, and luckily, we also grabbed this little model of, this is 5CV here. So here's 5CV, here's all the little atoms in there. Instead of modelling this as all my little atoms, I could just create a kind of average ellipsoid. So plenty of people do models where they take ellipsoids as a typical molecule. And then they can think of these ellipsoids as the fundamental components of a model, and they put a lot of those in the box and see what happens. Okay, so that will still need a large number of these molecules. We're not at the atomistic level, we're at the molecular level. And 10 to the 6 is the kind of figure you're seeing people doing molecular modelling. 10 to the 6 molecules is possible now. And you will be able to find some bulk properties, elastic constants, maybe some viscosities. And some people have been trying to model extremely thin cells. So, as in real devices. So my molecules keep popping up. And here's something that I did with a molecular modeler. This is a pneumatic between two, so I don't know what the distance between these two plates are, but it's sub-micron. You can't really make this device in reality. And the temperature here was cooled, and we found symmetric layering. In fact, there was a tilting of the symmetric layers. Okay, so that kind of thing can happen. We could instead consider what are called macroscopic quantities. So macroscopic quantities are representing a large group of molecules in a single average. Okay, so these quantities may then vary continuously through a sample. This sample is then called a continuum. It's a continuous system, not individual molecules or individual atoms. So for instance, here's my group of molecules. My ellipsoids have already coarse-grained, as it's called, into ellipsoids. Let's average all that. And the main property I can talk about is the pneumatic director. So I've averaged all that, all those molecules into a single direction, an average direction. Okay, and we can do this not just. So here's my molecules, maybe a lot more molecules, and you can see the average direction is slightly changing as we go. And so the average direction, the director, would change in space. Okay, so n now, which I've called my vector, which is the average direction, now is a function of x, some space coordinate. Okay, so this is a mathematical model. So another question we're going to get to. Let's go back to our Schlieren texture. We want to understand how these streaks interact with each other. But my question is, what's the most appropriate type of modeling? And you can answer now. Okay.
Okay, everyone.
47. People are waking up. Right, let's have a look. Okay, so a lot of people seem to have put continuum theory, which is all very nice because that's what it talks about. Quantum mechanics of this is going to be tricky, to be honest. So I've put a length scale on here, so 0.1 of a millimetre is a typical length scale for those kind of streaks. Think about how many molecules, how many atoms you have within a single streak, a single band here, across here, would be an awful lot of molecules. We couldn't really do a model at a quantum level, or even an atomistic modelling level. Really, continuum theory is probably going to be the most successful here, so D would have been the right answer. So a mixture, so quite a few people put a mixture, and that's interesting. There's an awful lot of people trying to do mixed methods nowadays, so-called hybrid modelling, and it might be true, particularly, as I'll come into later, if we think about defects. Now, defects are very small things, and it might be that at the centre of defects we need to use something different than a continuum model. So probably D or E is the correct answer there. Okay. So, you can see all the transitions are going to go crazy here. So we've gone from the molecular or subatomic level. Shouldn't have used your computers. And we can go all the way up to a device. So the length scale, let me see if we can get all these things on. Oh, nearly. So we can go from all the way down from the very small length scale, so this is supposed to be length scale from the angstrom to the centimetre, and from a very small time scale to a long time scale, all the way from molecular modelling all the way up to continuum modelling, and it's really only up there. I'm just going to get rid of this. I'm getting annoyed by the transitions. So it's only really at this level here that we're going to be able to model devices. An awful lot of you are probably interested, certainly engineers in the audience are going to be interested in devices. So that's where I'm going to concentrate. So for continuum theory, which is what Q-tensor is an example of continuum theory, we're going to have to develop using the appropriate dependent and independent variables. So I'll explain some of these terms. An independent variable is something that doesn't depend on anything. So it's something like space, coordinates or time, so they vary, time varies, space varies, I can go certainly 1 metre in this direction, 10 metres in that direction, but they don't depend on anything, they're fixed in some sense. I've got no control over them, so they're called independent variables. On top of that we have dependent variables, and these are all the things that you kind of don't know. So there might be the fluid velocity in a liquid crystal, or the director in a liquid crystal, and these might depend on the independent variables. Things might vary in space or in time. And they also might depend on parameters. And parameters for me, my definition is that these are quantities that are essentially constant in any single experiment. Okay, so the viscosity of a fluid might be constant in a single experiment, although Steve's experiment there where he heated up his liquid crystal certainly changed the viscosity. The viscosity of an isotropic liquid is different from the liquid crystal. Okay, so let's go back to our Schlieren texture. And so here we have an experiment. I'm imagining an experiment where the texture changes as we change temperature over time. So that's exactly what we saw just there with Steve. So what are the independent variables? Another question. Let's have a quick look at this. Do their clickers. So here we want the independent variables. I've already told you the answer, so hopefully lots of people are going to get this right. Click away. Remember, these are the things that we can't really change. It may vary. Last few people. Okay. Yeah, so that's interesting because certainly, well, A is correct in the sense that they are certainly independent variables, not all the independent variables. The reason is I'm changing the temperature with time, and so the most correct is probably B. My X, Y, and Z coordinates, because the structure you see underneath here certainly varies in space. It might vary in every three-dimensional space. Time is varying, we have no control over it. Now, temperature is not an independent variable because it depends on time. Okay? And so C and D are not correct. E is definitely not correct. It's at least A or B. Okay. That guy. That's a good question. Yeah.
Before defining the independent variable, you have to define dependent variable. What's the function? If you are considering the thermodynamic property, for example, enthalpy, the temperature will be independent.
Yeah, okay, so...
and also it's dependent on time.
Yes, so it depends what kind of model you're going to build. Yes, it does, it does. So, but the model of this experiment, you would expect temperature to be a dependent variable because it's externally imposed. The temperature sample that you're heating from externally, you're imposing the temperature on the sample. Now, if that temperature, yeah, okay, so if the entropy of the system varied in, well, yes, okay, so if I in a non-continuum approach, if I model using statistical physics, for instance, then it's a slightly different matter. In the continuum approach, we normally have temperature as essentially a parameter or a dependent variable, i.e. it's fixed externally, it depends maybe on time or space.
For example, you are going to do the modeling of the secondary stress in the continuum mechanics theory, okay? You are going to first solve the partial diffusion equation. For this domain, the temperature will not be independent variable, not dependent.
No, I might solve temperature as a dependent. It might be a parameter, of course, as well.
Yes,
but it might be, there would be probably a parameter. So it's something I can affect. Something I can affect. Independent variables for me are things I can't affect in any way.
For the distributing texture,
Yeah.
this is the metal plate. You are going to model the principal stress, for example. Okay. What's the independent variable in your modeling? Lambda Weierstrass model, the temperature.
I don't need an independent variable. I could have a zero-dimensional.
Always will be independent variable.
No. So my definition of independent variable is it's something that I can't affect. Okay. So I can't affect space. The coordinates in space. I can't affect those are fixed. I can't affect time. Time runs without me, doing it. Those for me are
How do you
my.
define your model?
Sorry.
How you define your model? You cannot say always the temperature is dependent. Depends to your modeling. What are you going to do?
Well, maybe. With my definition of independent variable, the temperature isn't an independent variable. It might be a parameter, it might be a dependent variable, but what
Might be. Is that the D might be right?
D might be right, okay. Well, maybe with a different modelling system, it might be right. Okay, so let's think about some dependent variables. So let me do this, and that. Okay, so answer. Press that twice. There we go. Okay, so you remember if we set our independent variables to be our spatial dimensions and time, then the question we're asking is what depends on those things? What depends on space? What depends on time? Okay. So there are lots of possible answers to this. In fact, I'm going to stop it there and see what you've done. Yeah, okay, so the director is clearly depending on space, and we can't see whether it depends on time because we haven't seen it dynamically, but it's clearly dependent on space because that's the optical texture here. The optics that we see, whether it's dark or light or coloured, is really telling us what the director is doing. So A is certainly right. B could be right, so the temperature B is right because the temperature is depending on time. It may also actually depend on space. There might be the heating from one side and not the other, and temperature then might depend on space. C actually is also true. We could induce flow. So we saw Steve inducing flow in his liquid crystal. So the flow velocity, the pressure, the density could all change in space and time. Electromagnetic field is also possibly true. Liquid crystals don't have to have an applied electric field to actually change the electric field. There could be intrinsically an electric field in there. And in fact, E, although no one answered it, there is lots of other things that could be dependent variables. And the key to model building is actually working out what are the most important dependent variables. And what are parameters? Well, we can answer this one if you want. Let's see what you say. So remember, parameters are things which, in a single experiment, I would imagine would be treated as constants. Okay? Now, sometimes this is hard to really work out whether they're constant, and the cycle of theory experiment really helps you decide what are constant. You might assume something's a parameter, and it turns out your model doesn't represent reality. It might turn out to be a dependent variable in the end. Okay, let's see what we've said. Yeah, so E, certainly all of the above are potential parameters. Well, they are certainly all parameters, and there probably are lots more different parameters. Okay.
Yes.
Yeah, sure.
You ask what are the parameters?
Yeah.
You don't define these parameters independent and independent variables. What's the definition of
A parameter. So my definition was before on the previous slide, and my definition of parameter was something that is constant in a single experiment. A quantity that is constant in a single experiment. Doesn't depend on independent variables at all.
For example, elasticity. You mean models of elasticity? For liquid?
A liquid crystal, the elastic constants.
Okay.
Yeah.
And when you change the temperature, the rate of the temperature change, the models of elasticity will be changed.
Yeah, so it could
as a parameter.
I
It's
can
not
totally.
a constant.
Yeah. Okay. So I could. Okay, so once we've got our variables, once we've got our parameters, we might want to build a theory. So, and really this tells us how the dependent variables might vary with the independent variables. So this theory might be a lot of, I'm not going to go into all these theories, I'm going to pick out one or two. It might be a balance of forces. We might think of conservation laws. So Navier-Stokes people might know about, and Navier-Stokes really are just a principle of conservation of mass and the principle of conservation of momentum. There might be an energy minimization. So energy minimization is kind of what I'm going to concentrate on. Here we build up an energy of a system, and we say the system wants to sit in the lowest energy possible. And so we want to find the minimal energy. The key aspect to all modelling, and people forget this a lot, is if we don't know X things, then we need X equations. Okay, it's relatively simple, but without that fundamental there, it's very hard to actually solve. Okay, so let's get on to some pneumatic liquid crystals. So pneumatic liquid crystals, what we think about are some dependent variables, and dependent variables here certainly are pneumatic director. So what we think about is a ball of molecules randomly oriented in this ball here, and when they become pneumatic, they get aligned on average in one direction, N. We could also think, rather than thinking about just a simple measure which is the average direction, we can also think of, let's imagine that theta m is the angle between the molecule and the director, and let's look at the spread of angles. So we know that on average it's 0, but there's a spread of angles either way. This spread we can actually measure, we can essentially measure the standard deviation or the variance of this spread. And this is what's called the order parameter, sometimes the scalar order parameter, often termed S. So these are two fundamentals of a probability density function for liquid crystals, pneumatic liquid crystals. It's defined S so that when S is 0, we have random orientation and we have the isotropic phase, and when S is not 0, we get a pneumatic phase. And so we can build models out of this. Actually, S and M fail to model some quite serious situations, And that's when we imagine our ball of liquid crystals all vaguely aligned in one direction. If we squash that ball a bit, then what happens is, if we look at our ball of molecules in 3 different directions along the x, y and z axes, they all look different. Okay, so if I've just kind of sketched this out, along the x-axis, I've squished this in the y direction, so along the x-axis they're going to constrain to not be vibrating as much. In the y-axis they can, they're freer to move, and if we look down on the z-axis, then we see a much smaller amount of orientational change. And these 3 different ways of looking at the molecule essentially mean what we have now is a biaxiality. Okay, so different values of the order parameter S depending on which way we look. Okay, so to measure, to model that kind of system, and this particularly happens near defects and near surfaces, to model that kind of system we need what's called a Q-tensor, and that's what the topic of this talk really is about. So particularly if you want to model defects, the Q-tensor is absolutely important. And I won't go into too much detail about exactly what the Q-tensor is. It's the second moment of the probability density function, and it's called the Q-tensor. We can take out of that certain things. We can take out of it a director n, but in fact there's a secondary director n, and now there are 2 order parameters. If we constrain the system, which often people do, you can actually get back a uniaxial system. Okay, so there are 3 different models I want to just briefly mention. I won't go into details at all. There's the model based on just a director, and that's the Frank-Ozeen-Zucker model. That we think about free energies like elasticity or dielectric energies written in terms of the director. There's an Ericsson model which was developed in the late 80s where you include this order parameter S, and the Landau-Vigent model, we heard about this yesterday from Tim Slukin, which is a Q-tensor theory. Okay, so there could be loads of other variables, loads of other dependent variables. There could be electric potential, there could be velocities, but I'm just going to concentrate on these type of systems. In fact, I'm just going to look at this one just now and build up a theory that we're going to use here. And I'm going to look at this Q-tensor theory just in a little bit of time. Okay, so how do we build up this elastic energy? We know certain things about the liquid crystal. Molecules prefer to align in the same direction, and so they prefer this top situation here compared to this bottom where we have some displaying of the director. And we want to model this in a function, functional. What we're going to do is we're going to assume that our energy is a function of the director n and gradients of n. So we're going to say that this non-zero distortion of n actually creates a greater energy. And to find this function, we need to, the specific function, we need to know things about the liquid crystal system, and especially the symmetries. Okay, so the assumption is how we build up an energy. I'll just briefly go through this. The director is so-called headless. Often you see directors as arrows. They're not arrows at all. They haven't got a head on the arrow. N and minus n can be exactly the same thing. So any energy we create, any function we create, has to stay the same if I swap n and minus n. Any translation of the system, so this bit of liquid crystal here, okay, there's a certain elasticity, it has an energy. If I move myself over here, I can't have changed that energy. So a translation, me moving this somewhere, can't change the energy. My energy that I construct has to obey that. It also has to obey the fact that if I turn my head, the energy can't change. So any rotation of my system also can't change the energy. And I'm also going to assume this is always used in these kind of theories, that any small distortion is going to give an energy, and there are no large distortions. So I go up to quadratic order in distortions. And after all that, I come out with this rather complicated looking formula for the elastic energy in an achiral nematic. There are 4 terms here, and you can see these constants, K1 to 4. They all represent a different type of elasticity. And in fact, the first 3 are easy to kind of think about. The first one's about displaying of the director of the molecules, the second one about twisting, and the third one about bending. And these elastic constants are very small, piconewtons. And you can see it's very easy to create elastic distortions in liquid crystals. If I go to an Ericsson type of elastic energy, what happens is I've introduced the variable S, and so S now comes in as or elastic constants now depend on S. There's one extra term right at the end here, which is about distortions of S as well. The energy I'm going to think about, although I'm not going into too much detail, is horrible looking energy, which is the Landau-Legendre elastic energy. This rather complicated energy models in exactly the same way as the Frank energy the elasticity of a liquid crystal system if it contains things like defects. Okay, there's one other thing, I'll just maybe skip over this a little bit. The thermotropic energy has to be included when I include my S, my order parameter, or Q as a dependent variable. Because once I think about S or Q, the order parameter varying in my liquid crystal sample, I've got to say what it prefers. And really this energy just says what it prefers. At high temperature, the minimum energy of the thermotropic energy sits here in the isotropic phase. It prefers to be isotropic. So at high temperature, I'm going to be isotropic. As I reduce temperature, this other state, the nematic state, is the preferred state. And there's a crossover, there's a first order phase transition between the two. Okay, so once we've done that, and it approximates it essentially as a Taylor series in whatever my dependent variable is. Okay, so I just want to skip that, and I'm going to skip those just for now. So how do we work out solutions? So we have an energy. I want to work out the minimum configuration that minimizes energy. What we do is we have to find a director configuration. It might be spatially varying that minimizes that energy. I'm not going to go into too much detail. This involves a calculus of variation, which I don't want to do a lecture on here. So just believe me that once I have constructed an energy, I can find the minimum energy using some quite sneaky techniques that were developed a few hundred years ago. Essentially what we get is a differential equation or a set of differential equations that need to be solved. For every dependent variable, I'm going to have a differential equation. And once I solve those, I can find the minimum energy configuration. Okay, so here's a relatively simple example. How long have I got? How long? When I should have ended about half.
Maybe an additional 5 to 10 minutes, and then you'll have a coffee break.
Okay, so a simple example, I'll just run through this one and I'll show you this. So here's an example, and there's some questions coming in a minute. I have two plates, and I've got my liquid crystal sample sandwiched in the middle of these two plates. On the bottom plate, my director is absolutely fixed to be parallel to the x-axis. On the top plate, it's fixed at an angle alpha, but I'm going to change that angle alpha. Okay? So we create some kind of distortion by changing this angle alpha. The elastic energy, when alpha is 0, you can see I've got basically no distortion at all. My elastic energy will, in fact, be 0. And I want to gradually increase my director angle alpha, the angle at the top there. So the question I have is, what's going to happen when I increase the angle alpha? And you can vote now. So will the elastic energy increase, decrease, remain constant, or something completely different? Anymore. Let's see how many people just want to speak. Well, 39's not bad. I'll do that. There we go. Okay. Yeah, okay, so most people say the elastic energy will increase, and that's exactly what we're going to see. In fact, D is also correct, and you'll see that in a minute. Something else does happen eventually. So the elastic energy does increase, so as I start winding up this director at the top, I increase the amount of splay and bend energy. And this is the picture of what actually happens. I've solved the system. My director N can now be written as simply an angle, the angle with the x-axis, and it changes as I go through the cell. The elastic energy I can work out theoretically is proportional to alpha squared. So as alpha increases, energy is increasing. And here's the picture of the energy going up as I increase my angle alpha. It's quadratic. With an Ericsson model, something completely different happens. With an Ericsson model, I'm allowing the melting of the liquid crystal. But what happens is, in very thin layers, as I increase, suddenly I reach a maximum energy, and then I start to decrease. And what happens here is I effectively have melted the liquid crystal. I've put in so much elastic energy But what happens here is suddenly it breaks. I break my liquid crystal, and all the top region becomes vertical, all the bottom region becomes horizontal, and right at the middle there is melting. And as I increase my angle a little bit more than pi over 2, so this is my angle here at pi over 2, it reforms as a nematic. I've melted it in the middle, and as my angle gets slightly bigger, I reform with the opposite sense of twist. So here I'm going anti-clockwise, and here I'm going clockwise. Okay, so this happens even in thick layers, as long as I have a model that allows melting. The nematic director model wouldn't allow melting, so I can do it for an Ericsson model, and I can do it for a Q-tensor model. I'll just give you a picture. So again, exactly the same as the Ericsson model. I reach a certain angle, and it starts to melt. Okay, so here's the first indication that the model, the type of model you choose is crucial. There's two different answers there for two different models. So I'll just do that. So in summary there, for this simple example, we absolutely need a model, for very thin layers, we absolutely need a model that allows melting. A simple Frank energy won't allow melting. So in 2 dimensions, I haven't got much time, so in 2 dimensions, you see exactly this melting. These defect structures here, so for instance, this picture here, these 2 brushed structures are these half defects, plus or minus a half. I'm sure you'll hear more about these. These plus or minus a half defects actually contain a degree of melting. If I go right through it, draw a line through this defect, I see exactly the same type of structure, this change in director orientation. And actually I'm going along an energy surface which, instead of melting, it's a form of biaxiality. And this is why the Q-tensor is very important for modelling defects. It allows biaxiality to happen in your model. Okay, and just one very quick thing about bistable displays. So a lot of bistable displays are out at the moment. They're very low cost in energy. They're very good in terms of how many pixels you can have. The bottom 2, the Kent State and the Zebedee, are certainly in production, and you can buy those if you want. I'm not sure about the top 2. The Zebedee device is the one which absolutely needs defects. Okay, so you cannot model the Zebedee device, and it was modelled right at the beginning when it was developed. You cannot model without using a model which has allows defects in. So Q-tensor theory is absolutely needed to model the Zebedee. And I think I'll stop there.
So we are behind the schedule, therefore I propose we just go and have a coffee break, and we will reconvene in some 15 minutes or so after this coffee break. And you can ask your questions, speaker will be